Good afternoon. Good afternoon, and welcome to the Concrete Institute of Australia. I'm John Nichols, Technical Manager for the Institute. It's my pleasure to be your host for this afternoon's webinar, Sustainability Through Methods of Construction. This webinar invites two young professionals to review sustainability by consideration and application of the processes and methods used for construction. The speakers are Daniel Prohasky and Melanie Langlois. I'd now like to invite Aaron Arathayan to introduce our two speakers. Ladies and gentlemen, please join me in welcoming Aaron.
Thanks, John. The first speaker we have is Daniel Prohasky, and the title of his presentation is Integrated Architectural Engineering of Sustainable Infrastructure. Daniel is a multi-starrer. He is a co-founder of Curvecrete, an architectural and robotics engineer. He is passionate about translating research towards industry adoption in Australia, particularly in the building, design, and construction industry. He is the founding lecturer in architectural engineering at Swinburne University, where I met him. And through his leadership with Curvecrete, he is on a mission to accelerate the transition to carbon negative and negative waste construction practices in Australia. He was recently awarded for his efforts in construction innovation and academic leadership as the Engineers Australia's Professional Engineer of the Year 2023 in Victoria. Ladies and gentlemen, let's put our hands together for Daniel.
Thank you very much, Aaron. And let me share my screen on my presentation. Okay, it's a pleasure to be here. Can I just do a check that you can see my screen okay?
Yes, we can. Yep.
Excellent. Thank you very much, John. So thank you for the Concrete Institute of Australia for this invitation to present to you today. This presentation will be on how we might reimagine sustainable infrastructure, particularly with concrete, and how we might shape that concrete in ways that are more structurally efficient to be able to use less material and achieve some sustainable outcomes with that. A little bit about myself and my background. I'm on a mission to accelerate our transition to a zero carbon, zero waste, and exciting future for construction. And in order to do that, I walk the tightrope of between architecture and engineering and academia and innovation. And as a architectural engineering lecturer in Swinburne University, we're able to share that with our architectural engineering students there in their undergraduate engineering course. I didn't really do this. This is obviously Photoshop. I think there's some laughter sound effects that should kick in now. On this journey towards how we create sustainable infrastructure, we need to consider not just the engineering principles about how to create more efficient structures, but also the design aspect. How does it look? How does it perform with other performative aspects, for instance, noise attenuation, etc., that we'll tap into throughout this presentation. So, just a little bit of summary about me personally. I was lucky enough to be Professional Engineer of the Year in 2023, awarded through Engineers Australia. That was a part of the fantastic work that my team at Curvecrete and the colleagues at Swinburne University have been up to, and I give all credit to them as well. What is Curvecrete? Curvecrete is a design consultancy. It's a manufacturer of curved concrete panels, and it's also a manufacturer of robotic molds to form those curved panels. Over the last few years, we've developed a geopolymer concrete, which a low carbon concrete that is about 70% lower carbon emitting, and we utilize that geopolymer with our robotic system to form this dual approach to how we create sustainable construction products. So this is why we do what we do. These two figures here, it's 8% of all global CO2 emissions, or almost 8%, are due to concrete, and Australia's construction waste figure is about 40% of the total amount of waste in Australia. So we're targeting absolute zero of these figures. And to do that, we're looking to reduce the amount of material use and use that low carbon material to achieve a combined reduction in carbon emissions. We can't do that alone, so it's a collaborative effort across industry and academia with lots of different players, and I just want to do a shout out to MECLA that you could get more involved with this conversation about how we introduce low embodied carbon materials into construction across Australia. So why curvature? Well, we can give the example of the Sydney Opera House here in Australia as putting us on the architectural international map, and it's Australia's icon. When you think Australia and architecture, you think of the Opera House and its beautiful curves. However, after almost exactly 50 years now, we haven't built something like this again, and that's due to the complexities around creating curvature, where with this example, the Sana Rolex Learning Center, they required 1,500 timber forms, and all of that timber creates a mound almost higher than the structure itself of waste and formwork. So how we reduce that formwork could be that we use a reusable method, and I'm going to introduce you to a method that we've developed using ruled surfaces. So I'm not sure if you'll be able to see this on the video screen. It might be a little bit small for you, but this is a panel that is curved. It's twisting around its orthogonal axis and creating a curve across the diagonal. And with this method, we're able to create, a completely reusable method of forming these types of shapes, and creating a series of bespoke panels that then can link together with straight edges at their edges. So manufacturing curved concrete panels using robotic formwork systems, and I want to give you a few examples of projects that we've demonstrated this with, and some of the challenges that we've had in specifying this for projects, etc. So just a little bit more introduction into what is a ruled surface, and its technical term is a hyperbolic paraboloid. It's a mathematical term. However, the ruled nature of it gives a series of straight lines, to form a twisted curve. So essentially, you can form, you can place reinforcement that is straight, but then achieve a curved shape. And once you achieve the curved shape, you can create a much stiffer, flat or almost flat surface. So a flat panel versus a curved panel on the right. Just a structural analysis showing 4 restraints at each corner, more or less, is demonstrating that you get about an order of magnitude stiffer panel when it's only subtly curved. So this one is about a 20-meter radius of curvature, and it's already exhibiting a significant reduction in deflection. So in terms of process, from the architect or a facade engineer, they'll be looking at rationalizing the facade into a series of quadrilateral shapes in that step 1, and then we're able to extract that mathematical information to then articulate a robot off to the right there. I might just get my laser pointer there. We use a series of different software to be able to do this, Rhinoceros and Grasshopper in particular, and then some other plugins to Grasshopper. And if you're not familiar with Rhino and Grasshopper, it's typically used by architects. However, these plugins to Grasshopper can simulate structural data, and a whole series of other engineering disciplines use this for environmental sustainable design, etc., for daylighting with different plugins and things. But what we're talking about here is looking at how we could iterate and integrate architectural data with engineering data so that we can achieve the mass optimized or reduced structures using the curvature. And then for architectural visualizations using Unreal Engine, which is the same software that is used to create animations for movies and things. So we go to a video just showing some of the visuals of what we might be able to create using these ruled surfaces, like liquid architecture, bridge structures, and maybe even stadiums. So the first project we called Nautilus. It's a spiral staircase that connects the top floor of a multi-residential building in Flinders Street. Essentially you've got the existing or what was existing on the left and what was proposed on the right. So created this access to the rooftop for the residents of the building. It becomes the only communal space for the residents. It's really enjoyed by the residents now. And went through the process of developing a system where we could decouple the structure from the cladding. The basics of the structural system is that we have a series of steel ribs that externalizes the steel reinforcement, and then we use fiber reinforced panels that are geopolymer panels and all bespoke shapes that hook into that structure. So then you end up with this rib-like architectural form in the external. On the internal, you get these panels or scales that clad the internal. There's 35 panels in this one that are all bespoke shapes and curved. So some of the challenges on this project were that how we were hooking the panels in. The tolerances were quite critical. How precise we were casting the panels was still in development because we developed the robotic system at the same time as casting the panels. So we wanted to develop that a bit further. So here you can see, maybe small here, there's some hooks that the panels had pins that then basically hooked onto. Yeah, we thought that we could maybe integrate that structure a bit further. So we went about creating a prototype facade system with a meeting pod. And instead of using just 2D drawings, we used 3D printing to actually demonstrate like how to communicate how this thing went together. Here you can see the literal 3D print that was the diagram to assemble the project. We went through this process of prototyping. So the connections, for instance, we wanted to make all modular. This is just a PVC pipe, just cut to get the geometric shape and a few coach screws. And then looking at threaded inserts and bolting steel ring. Then these two methods just being manual, and then tube laser cut, precision laser cut with a threaded bolt and locking pin. Then eventually got to a point where it was just the laser tube cut and hanger bolts that are kind of like coach screws on one side, but then a nice thread on the other side that you can put a locking nut onto. So looking at all those mechanical details, how that joint would come together. So then you end up with a system where you've got just one ring that rules them all. Yeah, a lot of the Rings fans. That is applied across the entire structure. So you can see the robotic system on the right with the rulings, and yes, I'd have to invite you over to the factory to show you more details of how this robotic system functions, but the output is here on the left, which is a prototype for the eventual meeting pod that was composed of 20 panels, and this a system that's similar to a cable net, but very tricky to simulate because you have a whole series of hinges. It's more like a mechanical system, but then once all the panels are in there, it locks that locks the shape. So then you end up with this rigid outer shell that is all tied in together. Okay, so we're going to do 2 projects quite quickly. Now, a little bit about the material and then how we might trial that on a facade system. So with some help from Swinburne researchers, we developed a high-strength superworkable geopolymer exhibiting these properties. So it's 50 MPa compressive strength, and it's got a high early strength for improved productivity, and the workability of it helps us to pour for structural applications in between reinforcement and achieve some quality finishes that are more controlled, and of course it's resulting in lower carbon emissions and uses 30% recycled material, which is made up of slag and fly ash. So the first trial project using this material will be a facade system. This will be eventually installed in Hawthorne, 760 Toorak Road. And there's a couple of panels here that are being created in the factory. So one of the challenges that we had with this project was how to cast vertically. So these were cast as is shown here in this orientation. And the reason why we want to cast vertically is to test out our capability in how we can achieve casting in any orientation, because once we go towards an infrastructure scale of curved panels, we would need to consider the verticality or the curvature of those panels. So yeah, and this is just an image of a jig that is defining a curve along the edge of the facade, which might be of interest. But yeah, going back to curvature, because we can create stiffer structures with curves, we want to see, what is the best application for this. It could be facades, like I spoken about a bit, but it could also be for freestanding structural walls. And we did a series of experiments with different shapes to see which might be more efficient structurally relative to its geometric shape. So here you see 3 different typologies, if you like: a diamond orientation similar to the meeting pod, the orthogonal direction, so just similar to just stacking tiles, and then a rhombus version, which exhibited less curvature. But we tested each one of these 9 topologies for wind and the leeward and windward directions, and found that the stiffest the stiffest and the one exhibiting the least peak stresses was the diamond orientation, due to its curvature in 2 directions, and creating that extra structural depth, to create a stiffer section vertically. So that's the example up the top there. So what you're seeing here with these color maps is the finite element analysis of each one of those configurations, where we've reduced the material thickness to achieve these maximum stress relative to the design stress. So this is at 73% utilization. Yeah, and this is what that type of noise attenuating wall may look like. And the result is that through the curvature and the increase in structural depth and stiffness from the curvature, is that we can reduce the amount of material that we use by about 50% relative to a straight or flat standard reinforced precast panel system. So yeah, there's a few different applications that we could apply this to, which we are testing out, and we'll be delivering on some urban furniture quite soon. And yeah, we have some plans to scale up production utilizing these noise wall concepts that we've been working on. And yeah, I'd love to hear any questions that you have about this process of trying to minimize the amount of material, utilizing curvature, and how we might specify reinforcement or other challenges around that. And yeah, keen to hear what you think. Thank you very much.
Thanks, Daniel. That was a fantastic presentation. Very, very enjoyable.
Thanks, Aaron.
Moving on to the second speaker, we have Melanie Langlois, and the title of her presentation is Concrete Sustainability on Major Infrastructure Projects. Melanie Langlois is a chartered civil engineer with a diverse background in construction engineering and specialization in concrete. She started her career with Bowie Building International as a site engineer in Switzerland. Subsequently, she transitioned to Bowie Construction Australia, continuing her infrastructure and public works subsidiary of the Bowie Group. She worked as a concrete engineer specializing in concrete technology on the Melbourne Metro Tunnel project before heading to the construction site as a shift engineer in charge of FRP works. She then joined the design team as concrete specialist, providing technical support across the entire project. She is also a PhD student at Swinburne University, delving into the realm of low carbon concrete with the objective to develop calcined clay-based geopolymer concrete. She now also contributes to other Bowie projects, providing concrete-related advice as well as assisting the tender team for future projects. It's a pleasure to have you here, Melanie. Ladies and gentlemen, join me in welcoming Melanie.
Thanks a lot, Aaron, for the introduction, and it's a pleasure for me to present at CIA NEXGen today. So I'm going to talk about concrete sustainability on a major infrastructure project. So I'm currently working on the Melbourne Metro Tunnel project, so I'm going to talk a bit about this one and other major projects worldwide that Bouygues Construction is working on. So I would like to start with the definition of sustainable solution. So this is the definition of Engineers Australia from Australian Engineering Competency Standard. And I'm going to read that to you. So developing sustainable solutions means you identify the economic, social, and environmental impacts of engineering activities and anticipate and manage the short and long-term effects of engineering activities. So that's what we need to do. So as we mentioned before, there is an issue with global warming, and the IPCC report, the recent one, highlighted that man-made CO2 emissions are the main cause of global warming, ocean acidification, frequency and intensity of heat waves, drought, precipitation, and flooding. 197 countries have signed the Paris Agreement, where we target to limit our global warming to 2 Celsius degrees compared to the temperature of 1850 by 2100. And an ideal target of 1.5 Celsius degrees. We know that the temperature will continue to rise until 2050. And in order to limit the global warming to 1.5 to 2 Celsius degrees, we need to drastically reduce our CO2 emission with a minimum of net zero value for CO2 emissions. So I invite you to read the VDZ report that was prepared to achieve net zero CO2 by 2050 in our cement and concrete sector. That's a very interesting report, so I'm not going to talk about that. What I want to mention is that today's engineering decision will have an impact on achieving our targets. So that's what I'm going to talk about today through our sustainable construction methods. We have to work together between design, construction, innovation. For example, from a design point of view, we need to optimize. We need to reduce the ratio of rebars. We need to reduce the concrete quantities we are using. We need to optimize the compressive strength, the characteristic compressive strength that we are using. Even try to achieve the compressive strength at 56 days rather than at 28 days. We can use performance-based specification. We can optimize our durability assessment, and we can also optimize the concrete mix development by using recycled aggregates, recycled water, crushed glass aggregates, high supplementary cementitious material content. Then from a construction point of view, the concrete mix selection is very important because it's going to have an impact on program, on cost, and also on the CO2 emission. We can also use alternative fuels, electricity over fuel, And then from an innovation point of view, we can trial new products. For example, limestone, calcine clay, concrete, geopolymer concrete. We can recycle materials as much as we can, reuse them. And we can also try to favor circular economy. For example, reuse excavation waste and try to make it geopolymer concrete, for example. So what I want to focus on today is the use of low carbon concrete through design and construction on construction site, the impact it's going to have on construction activities. So we have to work together. Here is the list of all the actors on a construction project, and we have to work hand in hand to make the use of low carbon concrete possible. So, for example, designers have to develop a specification, architects have to accept that low carbon concrete may have a different surface finish. Engineers have to work with designers, subcontractors to make the program work, avoid any delay. Subcontractor needs to familiarize themselves with new construction materials. We need to work hand in hand with supervisor, organize workshop, talk workforce through the use of low carbon concrete. Researcher can do like lots of research and work with industry and construction project to apply their research on major construction projects. We also need to work with clients, make sure that the product that we are developing is still compliant with standard and project requirements. And we can also work with concrete suppliers to make sure that we can achieve this. So I'm going to start with project requirements. So on a project, you will have different requirements. So it comes from the strength grade with a minimum compressive strength at 28 days. Then you also have to achieve a certain design life. So for example, on a major infrastructure project, it's most of the time 100 to 150 year design life with different exposure classification, internal, external. So you need to develop all this durability modeling. Then you also have a sustainability requirement, a certain percentage of cement reduction and replacement by supplementary cementitious material to achieve a certain sustainability rating. Then you also need to comply with fire resistance requirement, for example, against the RABTZ-TV or the hydrocarbon modified fire curves. Then you also need to make sure that the concrete that you're developing is pumpable through very long pumping distance. If you're taking the example of Melbourne Metro, for example, we had up to 1 kilometer long pumping distance all the way down into the tunnel. Then you also have, on top of pumpability, placement issues with reinforcement congestion, logistic issues, placement time, concrete consistency. Then you also have to make sure that you comply with the temperature requirements, maximum peak temperature and temperature differential. The temperature also has an impact on the stripping time and the program, and the temperature varies with the dimensions of the concrete element. Then we also have architectural requirements with exposed concrete element, front of house with class 1 or class 2 concrete finish. And then from a construction site point of view, we also have to comply with high early age strengths, minimum compressive strength for stripping, loading, setting time, as it can impact the formwork we are using, the program, when we can load the structure, when we can have plant equipment driving onto the structure. So we have to make sure that all the concrete mixes that we are developing are compliant with all these requirements. Then on top of that, you also have to comply with project specification and Victorian standard, Australian standard, and international standard. So what are the benefits and inconveniences that we have encountered on our projects? So I'm going to start with the benefits of using low carbon concrete. So using low carbon concrete means that we are using a high supplementary cementitious material content with like fly ash, slag, silica fume, or other pozzolanic material. and it will help with a lower heat of hydration. So for example, this is an example here of a very large concrete element. It was an 80 MPa concrete with very high amount of cementitious materials, and it was 3.6 meter thick. So as you can see, we were reaching about 80 Celsius degrees at the center. So we did some 3D and two-dimensional modeling to ensure that we would comply and that there will be no risk of delayed transit formation. So then using high SCM concrete can also reduce the carbon footprint. So we have sustainable concrete mixes, can get a higher sustainability rating for our project. Can also help with sulfate and chloride resistance. For example, in aggressive soil, where the groundwater contains elevated concentration of chloride and sulfate. So having a high slag or fly ash content can help with chloride resistance. Then it's also good for mitigating the alkali silica reaction. So for example, when we are having a reactive aggregate, using a certain amount of supplementary cementitious materials is required to mitigate the ASR. So here are the benefits. Now we are going to talk about all the challenges. And then we are going to tackle any of these issues with like, what have we done to prevent and mitigate these issues. So there is an issue with durability, with reduced carbonation resistance. Then there is another issue with slump inconsistency, because it's a little bit hard to ensure that these very high SCM mixes will always turn up on site with the exact same consistency. It's also really hard. We have some issues with slump retention, slump loss. It loses its slump very quickly, so we can use a water reducer and admixtures. Then there is an issue with like stickiness, flowability, rheology, pumpability. Then it can also impact the strength development. So there is a slow setting, there is a slower concrete hydration, and this has an impact on program. And then it also can have an impact on formwork pressure, because the pour rate of rise will be different based on the component of the mix design that we are using. So I'll start with durability. We know that high SCM supplementary cementitious material mixes have a lower carbonation resistance, and that we need a thicker concrete cover for high SCM mixes. So these are the durability report that we prepared on Melbourne Metro Tunnel using the Carbuff model and Live 365. And we can see that fly ash mixes required a higher cover than slag mixes. Then using a probabilistic approach with the FIB 34 model, we also saw that there is a thicker concrete cover that was required for high slag mixes, that we had issues with carbonation and chloride penetration, and that there is not enough data to have a very accurate model. So this is an example, an extract of the FIB 34 with the carbonation resistance coefficient. And sometimes you can see that it hasn't been determined. So what are the solutions for durability? We can use triple blend mixes. So not only like double blend with fly ash and cement or slag and cement. Using triple blend mixes will give us better durability results. We can also undertake laboratory trials, try to get as many results as possible when you're on the design phase of your project. Then you can also undertake in situ testing on long-term exposed concrete element to determine the chloride concentration at the surface, so that instead of using the predicted values in the model, you use the actual values on site in the area where you want to use this concrete. Then you need to combine and share the data to improve our models. So if we could like have a massive database with all this data available in Australia, that would be super helpful for consulting company and designers to develop a very detailed durability modeling. Then we can also test our concrete at 56 and 90 days instead of 28 days. It gives us better results. Then the issue with pumpability. I often hear that the concrete is very sticky, that we can't place it, that we can't pump it. And I have like workforce and supervisors on site struggling a lot with high SCM mixes. So what can we do for that? We can, ahead of using the concrete on site, we can do some pumpability trial. You can think it's going to like cost a lot of money, but then the money that you're going to save money later by making sure that you're in control of the concrete that you're placing. So you can use a very long line, use nomograph, and based on the output of your pump line, your pump diameter, your pump pressure, and the pump flow, you can determine the B coefficient, representative of the viscosity and rheology of your concrete mix design. Then you will know in any pump setup what the behavior of your concrete mix design will be. So that's what we have done on Melbourne Metro Tunnel for the second stage concrete mix down the tunnel. We had a 1.5 meter long line pump. We were using double AG pours, and that's what we did to ensure that the concrete that we developed was suitable and pumpable. Then we need to do pre-pour placement methodology. Have meeting with your supervision, subcontractors, engineers, everybody is aware of the placement methodology, where we are pouring the concrete first, what is our pour sequence, how many vibrators we need to use, what's the capacity of your vibrators, if we are using PVC pipes to make sure that the concrete is well placed at the bottom to avoid honeycombing, voids, concrete defect at the surface. So this is like working hand in hand with your with the workforce and the supervisory team. We can also do pre-pour trials. This is, for example, a trial that we did and that didn't go well, and that's how we were able to assess that that was the wrong concrete that was used, and that was the wrong formworks. Then a successful trial. We were testing different formwork release agents, different pumping methodology, for example, using a self-compacting concrete pump from the bottom to avoid voids, honeycombings. So you're in control of whatever you're doing on site. Then we can also use cold water to control the consistency and the pumpability of the mix. So, for example, during in summer, when the concrete is super hot, we can have complaints about consistency because the concrete is heating up very quickly. So if you're using cold water, you can control that. Then if you're using hot water, so I'm going to jump straight to the next slide. You can control the temperature, concrete placement temperature of your concrete, and it's going to have an impact then in this formula on the placement coefficient, and then on the maximum pressure that you can have on your formworks. Because we can see that using a high SCM mix will have an impact on the C2 coefficient. That's what we can see here. Depending on the type of cementitious blend that you are using, you will fall into a category. Depending on this category, you will have a certain C2 coefficient. So it's depending on either if you're using retarding and mixtures or high SCM mixes. And we can see in the previous formula that the C2 coefficient plays an important role on the maximum formwork pressure. So we don't want to delay the poor duration by having a mix that has a low setting time. So you can counter that by using hot water. Then I also often hear that we have an issue with delay in program due to the use of low carbon concrete. So this is an extract from Vic Road 610 because I'm in Victoria. You can see that vertical faces of walls and columns that are higher than 4 and 7 meters respectively, you need to wait 5 days to strip. We don't want to wait 5 days, and we are trying to optimize the program as much as we can. So we are using the maturity method so that we can use the compressive strength over the duration for stripping. So using the maturity method, using hot water, you're in control of what you're doing. So we start with a mix calibration so that we can get a relationship between the temperature and the strength of your concrete mix. That's how we end up with being able to prepare strength development and temperature rise modeling. So it's a combination of Syria C766 for temperature modeling. Now that we have also the maturity method, we are also going to use the ASTM C1074 for in situ strength development, and we can combine the two to predict based on the temperature obtained from the Syria 766 model the expected duration to obtain a certain compressive strength. So you can tell your construction team, okay, I'm sure that by using this low carbon concrete mix, you can still strip your concrete element within 24 hours without having a delay in your program. And then I'm going to talk about we saw in the definition from Engineers Australia that we also need to consider the economical impact of sustainable solution. So yes, low carbon concrete mixes are more expensive. You will need more workmanship to place and pump the concrete because it's sticky. It will require more vibrators. It will require more workforce. Then the duration of the pour can be also slightly slower due to a lower pumpability and a lower pour rate of rise. You can experience program delays, and then you can also have expensive admixtures or activators to have a higher strength. But in the future, we expect to have carbon taxes. So it's soon to come in Australia. Reading the latest articles from economists, we should see governmental policies anytime soon with a carbon tax or a levy on fossil fuels or country penalties. You will get fined if you're not achieving targets. And there will also be like climate energy contribution and funds for companies that are achieving their targets. So, okay, it's maybe more expensive now, but in the future, I think it's going to be more expensive to use high CO2 concrete mixes. And we have seen in this presentation that we can prevent an issue with using high SCM mixes. So it's our responsibility today to achieve net zero by 2050. I'm going to end my presentation with an example. These are CO2 emission factors on tunnel segments on the different tunnel projects from Bouygues Construction. So you can see that in 2022, we were very high in terms of CO2 emissions. In red, we have like concrete mixes using rebars. We can massively reduce our CO2 emission by using steel fibers. So that's a design optimization. Then if we use supplementary cementitious materials, we can see that we are also reducing our CO2 emissions. So this is where we are at on Melbourne Metro with a 50% cement reduction and replacement on our tunnel segments. And we can do even better on the latest project where we are using up to 65% cement reduction and replacement. So we decide today what we can do to achieve our targets. Thank you very much.
Thanks, Melanie, for this excellent presentation. It's super detail oriented. I've been taking notes from the first slide. Let's move on to the questions and answers section now. We have a few questions from the participants. Let me quickly go through it. I think the first question is from Jay Tiltman from Giorgio Group. I think the question is for Daniel. And the question is, what thickness are you able to achieve and what type of reinforcing is embedded within the curved panels?
Hey, thank you for the question, Jay, and for Aaron to repeating it very well. Yeah.
Yeah, the question is, what thickness are you able to achieve
Yeah.
with this robotic technology, and what type of reinforcing is embedded within the curved concrete panels?
Yeah, so because of the nature of the rulings, the geometry is ruled. So there's a possibility to include longitudinal, latitudinal reinforcement in each ruling direction, orthogonal to one another, more or less. And yeah, so you can use straight sticks of reinforcement. The thickness that we're achieving on the engineering design for the freestanding noise walls at a 9-meter height is 150 millimeter thick, and that's really just the restraint of obviously the stress distribution, but also how much cover we require, how much reinforcement we can fit within that small space. However, we've been working on some ways to reduce the amount of reinforcement that we're going through engineering process now, where we're looking at continuous strand fiber reinforcement to reduce some of that steel reinforcement in areas where it's considered as a non-structural portion of the wall, where you can achieve structural stiffness in some portions of the wall, but then span between those structural elements using an alternative reinforcement method using continuous fibers, which is under development.
Yeah, thanks, Daniel. And another question, I think that's for Melanie. It's from Paul Wins from WSP. And the question is, if the cover is increased to mitigate the risk of carbonation, and is the volume of concrete increased? And if in that case, is there an environmental benefit, or is the environmental benefit reduced?
So yeah, no, that's a very good question, and but we need to consider both cases. Is it better to use conventional GP cement mix, and in that case we have normal concrete cover, or if we use ISCM mix, then we have an increased cover. So we have done some calculation on a recent project, and at the end it was it's going to depend on the dimension of your concrete elements, but if you can avoid a lot of CO2 emission by using a low carbon concrete, the difference in like a few millimeters of cover is not that impactful. So it's better to use low carbon concrete at the end.
Yeah, I have a couple of questions for each of you. I ask one question for each of you. Melanie, while you're there, what measures do you use to calculate the reduction in carbon in these large-scale construction projects? It always comes with multiple coefficients, and some people use it from supplier data. So what kind of data you look when you look at a large-scale project?
So it depends on the project, and we need to compare apple with apples. So for example, in Australia, we use the ISC numbers from the Infrastructure Sustainability Council of Australia and New Zealand, and they have this CO2 emission based on the different strength grades and the different percentage of supplementary cementitious material that are used. There are like other calculators. We can also use the EPDs from the subcontractor, so that's the actual data. And so that because for example, if you're looking at European project and that you're presenting your numbers done with the ISC calculations, then you can compare the CO2 emissions because they are not using the ISC values over there. That's why it's always better to ask the environmental product to ensure that you're comparing the right values.
Okay, thank you. Thanks, Melanie. And last question to Daniel. Daniel, normally the concrete takes about 24 hours or more for it to finally set and become stiff. So does this affect the speed of this curved panel production? And do you look into ways to speed up the process?
Yeah, absolutely. So the geopolymer that we're using is high Li strength. So within 18 to 24 hours, we can demold the panels. From a production perspective, from like a precursor perspective, this has some trade-offs. So to achieve that high Li strength, the open time is reduced, which causes a challenge in how you can get the material into the mold quick enough. But the benefit is that you can demold quicker with larger panels. And what we've been doing is experimenting with how much control we have over the open time with different processes or methods of mixing, with the order of materials in which are being mixed to activate the reaction at a later time, and using retardants in that process as well, and also looking at ways in which we can change how we're getting the material into the mold itself. So reliably mixing, but then rather than just pouring it in, actually injecting it in from the base, and controlling the quality of the mix in its output.
Yeah, that's fantastic. That's all from us. I'll give the mic back to John.
Okay, good. Thanks very much. And ladies and gentlemen, I'd ask you to join us in thanking our three speakers for certainly a job well done: Aaron, Daniel, and Melanie.